Good afternoon. It is, let's see, 1.2, day number 2, symmetry, graphically and analytically. Let's go. I don't know what these things are supposed to be or why they're here. Is this a Chuck E. Cheese coin? What is this? Okay, ancient Egypt. I have no idea why it's there. Some of these slides come from Doc Sauer. I like take some of his stuff. You know Doc Sauer? He's a doctor in math. I'm not. So this probably has deeper meaning, but I don't know what it is. Hey, your Venn diagram lab is due Friday. Friday. Okay, so start thinking about that. Okay, let's talk about symmetry. Yesterday we talked about these 3 rules. Okay, these 3 rules. If a graph has x-axis symmetry, we do this transformation. Okay. Okay, xy, a point, any point xy, if it has x-axis symmetry, will also have a point x negative y. Okay. We said what about this? Can it be a function? No, not happening, right? This is not happening. There can't be an x that has 2 different y values or outputs. Okay, cool. Y-axis symmetry. If I have a point xy, that means there's also a point negative xy. Okay, could that be a function? Sure, yeah, it's definitely could be a function. Like, for example, this graph. The absolute value of x, negativized, right? Made negative. That's not a math term, okay? Likewise, on the previous example, the square root of x looks like that-ish. Could try. And the negative square root of x looks like that. Well, that's no longer a function once I add that second stem to that graph. And then this one's funny, but if you have a point xy and this relation, in this case it is a function, but if this relation has origin symmetry, then there's also a point negative x negative y. The sine function, and this is not going to be drawn to scale, but the sine function looks something like this. You may have seen this last year, but maybe not. Did you? A little bit at the end? No? Okay. A little bit of trig. So this point right here, let's call this point, I don't know, let's say pi over 2, comma 1. This point would then be negative pi over 2, negative 1. Look at the symmetry there. That could be visualized as a reflection over both axes, right? Reflection over the y, then over the x, or rotation 180 about the origin. That's what origin symmetry is. So far, so good. Okay, that's an intro. It's kind of what we did yesterday. Let's test this symmetry graphically. Tell me that we did this in our warm-up. We didn't. Yuck. Okay, let's do this together. Let's find the x-intercepts. X-intercepts are where y equals what? 0. So if I'm looking for the x-intercepts, it's where y equals 0. I'm going to cross this out, right? Because y equals 0. So if I divide by 4, what do I get? 8. So x squared equals 8. So x equals plus or minus the square root of 8, which is reducible. So a non-JV answer would be 2 root 2. Plus or minus 2 root 2. So our x-intercepts, of course, are where y equals 0. So our x-intercepts would be as follows. 2 root 2, comma, 0, and negative 2 root 2, comma, 0. All right, what is 2 root 2? Well, it's really root 8, which is a little less than 3. A little less than 3. So here we go. Positive 3, 0. A little less than negative 3, 0, or a little greater, sorry. And we've got them. There's our x-intercepts. Let's do the same thing for y. Okay, so get back up here, erase this red x, and now when We have a y-intercept, our x equals 0. If I divide by 2, I get 16. Oh, thank goodness. All right? Because the square root of 16 is 4. So I've got two answers here. 4, 0. Whoop. Back it up. X is 0. Y is 4. X is 0. Y is negative 4. I've got two y-intercepts at those 2 points. Now, you can anticipate this is actually the form of an ellipse. Okay? This ellipse is elongated in the y direction. What did I do? No, I did it right. We're good. It's going to look like this. So does this graph have x-axis symmetry? Sure. Yeah. I got up here, I've got 0, 4, 0, 4, and down here I've got 0, negative 4. Sweet. So x-axis symmetry, of course I would have it here. This is x-axis symmetry. Yes. I could test it in a couple different ways, or I could just look at the points. Does it have y-axis symmetry? Yeah, the two red points reflect directly on each other. So y-axis symmetry, that's symmetry. Right there. Yes, it does. Yes, it does. Does it have origin symmetry? If I rotate it 180 degrees, does it line back up? Yeah, it does. Let's take a point. Let's take this point. Let's take x equals 1. If x equals 1, what did I do? Pause. If x equals 1, I would have 4 plus 2y squared is equal to 32. Let's just do some math here and simplify. So I'd subtract 4. So if I subtract 4, I get 28. 2y squared equals 28. And if I divide, then y squared equals 14, and then y would equal plus or minus the square root of 14. Whew. Okay. So when x equals 1, I get root 14. When x equals 1, I also get negative root 14. What do you think would happen if I plug in negative 1? I get negative root 14. And if I, that should be a positive. Whoops. And if I plug in negative 1, I also get negative root 14. This is a dumb example, Mr. Ludd. It has all symmetries. Yes, it does. Yes, it does. If I give you a circle oriented or centered around the origin, you should say, what is this? This is easy, right? Because, yeah, I can flip it this way, or flip it both. Whoa, hold on. Did anybody just have a moment? Did anybody just have a moment? If it has y-axis symmetry and it has x-axis symmetry, then it has to have origin symmetry. That was an explosion. I just didn't want to, hurt your ears. If it has x and it has y, then it has to have origin. Yes, sir. If it has origin, does it have to have x and y? No. No. Go back an example. This has origin. Does it have x? Does it have y? But if it has x and y, it has to have origin. Good question. Okay. One more thing here, and I think this is the end of the notes. This is unbelievable. This is great. Analytically, how do we do this? Analytically, what does that even mean? Without numbers. So this might take a moment for you to kind of understand. But here's what I'm going to do. That's blue, not purple. Okay, blue. What I'm going to do is I'm going to plug just x and negative y into the original, and I'm going to see if I get the original back. Okay, well, that might be like, you're not gonna, and I see it too. It's not going to happen. But if I plug in negative y in for y, and I leave x the same, no change, and then I attempt to get this to look like it used to, I can't do it because I either have this or I have that. And neither of those is equivalent to the original equation. So because these two, that and that, are not equal to the original, it doesn't have x-axis symmetry. Okay, I've gotten these two things. I manipulated using a negative y, and I couldn't recover the original function. So it doesn't have that x-axis symmetry. Okay. What if I go the other way? I try y-axis symmetry, right? So now what I'm going to do is I'm going to take the original function, and I'm going to plug in a negative x. Well, when I simplify that, if I cube a negative, is it negative or positive? Negative times a negative is a positive, times a negative is a negative, right? Odd powers are still negative. So I have a negative x cubed, and minus a negative gives me a plus x. Is that the same as the original function? No. Answer is no. So for similar reasons, I'm going to copy this. I'm going to make it red. And I'm going to change that to y. Now, are we all just waiting for origin symmetry to work? Yeah. It's going to work, guys. I hope. Let's see what happens. Let's plug in a negative y. Let's plug in a negative x. Let's simplify. We've seen some of this before. That's not right. Yeah, it is. Because when I change that left side to a positive, it changes everything on the other side to the opposite. Oh, pyong. Therefore, yes, origin symmetry. So, Luca, there's your example. Algebraically. Cool. Okay, I believe we go to homework next. So I'm gonna drop the mic while it's hot here before 15 minutes hits because I am not what they call verified. So I can't go over 15 minutes. Oh, I still have like 32 seconds. What? I have a cool weird skill. You ready for it? When I was little, we lived in Chicago and we'd drive to Minneapolis to see my family. I'm trying to talk fast. And I couldn't sleep in the car because my sister would sleep and she'd snore and my brother's feet stunk. So I asked my dad, I'm like, Dad, what do you do? This is like a 7-hour drive. What do you do? He said, I read billboards backwards. So I would read billboards backwards for like 6.5 hours straight. So my favorite combination of words is Wisconsin Dells, which is Nisnoxu sled. Minneapolis is Silapayanim. Minnesota is Atosinim. Comiskey Park is Krapyaksamak. My name backwards is Noskvdal Kram, Yurahakaz. Shoot.